everyone, I'm Sparshit and I'm an educator at E-Level, and today we'll be looking at this problem called redistribution. Let's jump straight into it. Okay, the question is, you just met Buzz Lightyear. He has found an infinity and beyond box which contains an unlimited supply of odd numbers from 3 to infinity but has no ones. Right? So 3, 5, 7, so on till infinity. Your favorite number is X, and you want to know how many sequences Buzz can create from the infinity box that sums up to your favorite number X. So we have a box of numbers that starts from 3 and increments by 2, which is 3, 5, 7, 9, 11, so on and so forth, every odd number until infinity, and we have a number X which we need to reach. Formally, how many distinct sequences you can form from the numbers in the box whose sum is X. Right? So this is what we essentially need to do today. Since the number can be very large, print it modulo 10 to the power of 9 plus 7, which is a standard rule that we follow whenever the output is very, very large. And the value of X, as we understand, should be from 1 to 2000. Right? And input format is fairly straightforward. You will only have one integer X, that is our favorite number. And the output format is again very simple. We just need to print the total possible number of subsequences that add up to our favorite number X. And of course, if the integer is very large, we will do modulo of 10 to the power of 9 plus 7. Right? So let's understand the problem statement. Bases are sample input and sample output, which is if the sample input is 9, the sample output is expected to be 2. Right? And the sequences are supposed to be 9 and a bunch of 3s. Now let's take a look at how to approach this problem. Yeah. So we have the number 9 right now, and we have the set of numbers, odd numbers, let's say 3, 5, 7, 9, 11, 13, and so on. Right, till infinity. All odd numbers. Right? So now how do we know how many number of combinations exist in this set of numbers in order to get to 9? What does our intuition say? Right? Let's take a look at the naive approach itself first. Let's say that we want to try out every possible combination. Now how would we do that? Right? So let's say I pick 3. I make the decision to pick 3. If I pick 3 out of 9, right, I have to reach 9. If I have picked 3, then the next number I would actually have to reach is actually 6, right? Because if I have already picked 3, then the total value that I have left to pick the other numbers would be 9 minus 3, right, which is equal to 6. Right? So now that I have gotten to 6, again I have the same set of choices to make. I can pick between 3, 5, 7, 9, 11, 13 till infinity. Right? So let's say again I want to try out every possible combination. So I start with 3 again. Right? What would our logic be then? What would be the resultant output? I'll have to do 6 minus 3 because I made the decision once here to pick 3, and here again I'm making the decision to pick 3. Right? And same here, I make the decision to pick 3 again because this is at the starting of the choices that I have. And then if I pick this again, I hit 0. Right? So whenever I hit 0, I know for a fact that 9 can be reached if I make these 3 choices. Right? So if I make these 3 choices, I'm able to get to a 0 state, which means that I went from 9, I made some choices and I hit 0 because that's the total amount that is left to me, which means that 9 is reachable with these set of choices. Now at every step, I can make any of these choices, right? So here, for example, I could have, instead of 3, chosen 5, right? So let's take this example. If I had chosen 5, then the next set would have been, take this here, I chose 5, right? So what is remaining now in my set? 9 minus 5, right? 4. Now again, I start with all our choices. So I have sketched out 3 in the first set, but in the second set, now again I'll start with 3. Right? So I start with 3. So I pick 3 here and I hit 1. Now, when I go back to pick from the entire set again, from 1 to go even lesser, the moment I pick even 3, right, I hit off -2 or some value that is less than 0. Right? The moment I hit some value less than 0, I know that these set of combinations cannot reach 9. Right? So if I've already picked 3 and if I've already picked 5 and 3, then I already have the number 8. So whatever I pick from this set will not hit 9, right? Because it will not, the moment I go to negative, it means that I've already exceeded my limit of 9, right? So then I come back, then I say, okay, boss, I cannot reach 9. Let's try some other value here, right? So instead of 3, again, I pick 5, right? But the moment I hit 5, here only I reach of greater value than 9, right? Because I hit 10. So 5 plus 5, so I already had 5 and I cannot hit 9 anymore because I get -1 here only. Right? So we realize, okay, 5 also cannot be the choice. So then we go back, right? So we realize, okay, if I start with 5, then there is no point. I will not reach 9 again. So let's start over, right? So now our set was 3, 5, 7, 9, 11 and so on. We have already encountered 3 and 3, 3, 3, which was one combination to hit 9. We realized from 5 we cannot do anything. Let's repeat the same exercise. 9, and then let's say we picked 7 as the first choice. Right? We picked 7 as the first choice. Now the remaining amount is 2. And whatever I pick here, let's say even if I pick the first element, 3, I will still hit -1, right? Because 2 minus 3 would be -1. So even 7 is a bad combination. Right? Now the only value that I have left is 9. Right? And the moment I pick 9 as the first choice, I already hit 0 state. Right? Which means that this is a valid combination. So I can pick 9. Right? So this again becomes another possible combination. So if I choose any number after 9, right? Let's say I choose 11. 9 minus 11 in the first step itself becomes -2. Therefore, we know that we cannot pick -11 as a choice. So we are all out of options. Right? So we can conclude that 1 plus 1, 2 is the total number of possible combinations if I have to reach 9 from the odd number set that starts from 3 till infinity that we have. Right? So if we go back to our test case, this is what it says. Sample input is 9 and sample output is 2. Okay, so how do we model this? Let's start by keeping a variable current sum, which would keep track of what choices we have made so far. We'll keep adding to this sum as and when we make every choice. So we select, in this case, let's say we make the selection 3, right? We say out of the bag of numbers, I want 3, right? Again, to reach this number 9, right? So current sum becomes 3. And then if I make another choice, that I will again select another 3, right? So then current sum becomes 6. Then I say I may want to make another choice 3. So then current sum becomes 9, right? So the moment we hit 0 state, like we have discussed, we can just say that this is one possible combination, right? And let's take the other example where the first choice we make is 3, right? So current sum becomes 3. Second choice, instead of making 3, we try with 5, right? So now current sum becomes 8. The third choice we make, again, let's say we make the choice 3 because we want to start from 3 again. We realize that now the current sum is 11, so, but 11 is already greater than 9 and we didn't hit 0 state. So we know that this is not a possible combination, this is a possible combination. Right? So we make all such possible combinations, we go through them, and then if we sum up, whenever we hit 1, we take it as 1. Whenever we hit this condition, we take it as 0. And if I sum up these ones and zeros, I will get all possible combinations, right? Sum of all possible combinations. So let's just model that. So we need to keep a current sum 0. Now we have our breaking states as well. If current sum equals to n, then we know we want to mark it as 1. If current sum is greater than n, then we know we have overshot it. So we want to say no such solution exists. Let's keep possible solutions count to keep track of how many ones and zeros we have. Right. So then we iterate through every possible decision at every step recursively. Right. So let's keep this as 3 because we are starting from 3. We want to go till n because including n, because let's say if there is a value 9 itself is a possible combination, and we want to say I is equal to I plus 2 because we are only taking odd numbers, right? So possible solutions count simply becomes a sum of all of my choices, which is find all possible solutions count. And here what do I pass? Here I pass a decision that I've made, and current sum plus I, where I is the decision that I've made. Okay. So this looks good. We just need to pass the current sum around recursively since we are passing it here, as well as add it here when we are initially calling it where the value is 0, and I think this should work, right? So let's execute and see if everything looks good, right? So we've got the value 2, right, which is what we had expected. These are the two sequences 9, 3, 3, 3, like we had expected. Right, now let's go through some of the other test cases, and this is where it gets interesting to see if our problem scales well with larger test cases. Right, so let's take this input 90. Right? Instead of 9, let's make it 90 and see if it works. Right. So now we see that our solution, which is giving the correct answer, does not scale very well. And it is taking a really long time because we are going through all the possible combinations. Right? So I would say at this point of time, please pause the video and try to figure out how to make this more optimal, and then let's discuss the solution. Okay, in order for us to optimize this, we just need to come to one realization. The one realization that we have to come to is that at different current sums, right, we are capturing whether a possible solution is already present or not. Right. So if when I'm going through recursively 3 to 6 to 9 and then returning from 9 to 6 to 3, I am already calculating what is the current sum, what is the possible solutions at 9, at 6 and at 3. Right. If I made these choices at these current sums. Right. So the fact that we have to utilize is that we have already computed current sums for all of these, and if we find a way to store them at a later point of time when we need the current sum of this, we don't need to go through everything, every recursion, and we can return early. For example, at the end of this, these possible combinations will come to a point where our first choice itself will be 9. Right, like our first choice here was 3, and then later we'd make the first choice as 5, and so on and so forth, like we have discussed before. Then we'll make 7 as the first choice and go till all the possible combinations, and eventually we'll come to a point where 9 will be the first possible combination. And instead of saying CS equals to 9, let me try and find out what are the possible combinations that will hit 9 with 9 by doing all our calculations. We simply know that we have already calculated this before here. So let me just use that and say this is one possible combination which we have realized here, and that is the way to pre-compute and store these values. Right? So if I have to do this in code, what do? I just maintain an array, right? Let's say DP, which will have n elements, all initialized to -1, because I don't know how many possible combinations reach each number. I'll just assume for now it doesn't reach this number, right? And whenever I hit possible solutions count for that number, I simply start storing it. Right? So I simply say dp of n dp of current sum equals to possible solutions count, right? Because I know at that current sum, this is the number of possible solutions that are available, right? And another thing that we didn't do last time was use mod, because we will encounter large numbers when you have larger inputs, right? And then we simply return the same here as well, right? And whenever we encounter this, before we get into all of this and start recursing, we simply check, have I encountered this before? If I have encountered this current sum before, let me just simply return that value. So now how do I know if I have encountered it before? We have pre-filled it to -1 and we are setting it to a value if it exists, right? So we simply say, let me just know that if I ever reach this number, I know what is the total number of possible solutions till that number, right? So I can simply return dp of current sum, right? So if I do this, then we can cut down a lot of recursions, because we don't need to go through every possible combination as long as we have hit the right current sum before itself. And so if I run this now, we will get 342153243274. If we take a look at this number here, this is the same as this number, right? So to summarize, what did we do? We realized that if I am going to go through every current sum combination, right, we already get some we already hit multiple numbers before. If you're able to store that in an array, dp, where I say dp of 9 equals to 1, because I know at 9 there is a possible combination 1. Whenever I hit that current sum again, I simply slot that in and say I've already computed that before, please use this, instead of recursing again and again, right? I hope this is clear. I hope I've helped you understand better concepts of recursion and how recursion can be optimized using DPL. Right? Thank you.